5.3 Daily Check. Number 1. What age groups use social networking sites? A recent study produced the following data about 768 individuals who were asked their age and which of 3 social networking sites they used most often. People who did not use such sites were excluded from the study. Suppose one subject from the study was selected at random. Part A, find the probability that the selected subject preferred Twitter. So we look at how many total people liked Twitter, 244. I'm going to say the probability that you liked Twitter is going to be 244 over the total number of people, 768. You should simplify that, 61 over 192. Change it to a decimal, 0.3177. Okay, change it to a percent. So no, I'm not requiring you to have all of these answers. I will accept this answer, I will accept this answer, I will accept this answer, or this answer. So, some fraction, simplified fraction, decimal, or percent will be fine. But the thing is, you have a multiple choice test, so you really don't know which format the answer choices are going to be in. So you need to be familiar with all of them, okay? Part B, find the probability that the selected subject preferred Twitter given that he or she was in the 45 to 64 age group. So we only care about these people. We don't care about these, we don't care about these, we don't care about these, okay? Because it is given that they're in that age group. So nobody else exists. So who likes Twitter in that age group? 81 out of the total 290. So the probability that you like Twitter given, remember the vertical line means given, that you're in the age 45 to 64 age group is equal to 81 is the ones in that group that like Twitter, that age group that like Twitter, out of 290 total people in that age group. So that's one format of the answer. Then we could change it to a decimal, 0.2793. Or we can change it to a percentage. So 27.93% would also be correct. Okay. Let me erase what I have up here. Are the events preferred Twitter and age group 45 to 64 independent? And explain. So the rule for independent says if I have the probability of A given B, it has to be equal to the probability of A. And if that's true, then I also need to prove, I got to switch it around and say the probability of B given A has to be equal to the probability of B. I didn't use A's and B's on parts A and B, but given the problems that I did in parts A and B, I have proven probability of T, that would be part A, is not equal to the probability of T given the age group thing. Okay, so I'm just saying age there. That's already not true because we have, so we'd say no, and it's good enough just to say that 244 over 768 is not equal to 81 over 290. Or you could put a decimal format. You could say 0.3177 is not equal to 0.2793. So we've already proved they're not independent because the given is not equal to the just probability of the first event. Okay, part D, are the events preferred Twitter and age group 45 to 64 mutually exclusive? Again, no, they are not, but it's a different reason this time. If we're looking at preferring Twitter and age group 45 to 64, we need to ask ourselves, is there any overlap? These 81 people are both in the Twitter group and in the age group. So no, there's overlap. Between the events would be good enough. And make sure that you give like who's in that overlap. So I'm just going to say there's overlap. And here I'm going to say the 81 is the one that kind of messes it up for us. Okay, part B. I'm sorry, part E, excuse me. If a random sample of 2 subjects were selected, what is the probability that neither preferred Twitter? So the first person, and we're back to just out of everybody, okay? It doesn't say in a certain age group. So the very first person has if we look at who likes Twitter, 290 of them like Twitter. Excuse me, again, that's the age group. Sorry about that, guys. So Twitter, 240 people in my alignment. It's all 244 like Twitter. So we're going to say 768, which is the total. $768 is the total minus the 244 that like Twitter. That's going to leave me with 524 people that don't like it out of the total. Okay, let me kind of talk you through that again. So if 244 like it and I subtract it away from the total, then that leaves you with the people that don't like it. I also could have added the 308 and the 216, which you should notice also adds to 524. So either way is fine. Subtract from who does like, the total, how many like it from who the total people, or you can just add the two, Facebook and LinkedIn, together. So anyway, this is the first person's probability of liking Twitter, but you've already used the first person's, or not liking Twitter, excuse me. So then you go to the second person. The second person, there's not 524 people that don't like Twitter anymore. Now there's 523 because you've already used the first person. So now you have one less. Same thing for the total. It would now be 767 because you're doing two people. Okay. So if I multiply these two fractions together, I get 0.4652. Okay, which gives us about 46.52%. Number 2, some days Raymond drives to work. The rest of the time he rides his bike. Suppose we choose a random work day. The following table gives the probabilities of several events. Find the probability that Raymond is late for work given that he drives. So I'm going to define some variables here. So I'm going to let NL be not late. Let me see, write that. So then I'm going to let L be late. Sorry, guys. You're driving me crazy. I'm going to let DB drive. And then I'm going to let BB bike. Okay, so find the probability that he is late for work given that he drives would be probability of L given D. And so according to the formula sheet, I mean, it's got A's and B's, but if you change all the A's to L's and change all the B's to D's, then we have the probability of L given D is equal to the probability of L and D divided by the probability of D. So the probability of L and D would be the 0.05 given to us. Okay, divided by the probability of just D, which is given to us as 0.2. Okay, so we do 0.05 divided by 0.20, and we get 0.25. So that's the answer for part A. Part B, find the probability that Raymond is not late for work given that he drives. The probability that he's not late for work given that he drives. Okay, so we could go through the formula again, or we can realize that A and B go together. They're both given that he drives. So if he is late 25% of the time, then it leaves us with 75% of the time for him to be on time or not late for work. Then they ask us to draw a tree diagram. And so to get to work, he either drives or he bikes. So I'm going to start there. Okay. And so we found out, or we can look at the top and say, okay, he drives to work 20% of the time. So that means he bikes to work 80% of the time. We're going to assume those are his only two options. He either drives or he bikes. Okay. And then off of the driving, we found in part A that he's late 25% of the time. We found that he's not late in part B 75% of the time. When he bikes, that's given to us here. When he bikes, he's late for work 30% of the time. We're just going to have to ignore that line that it created, okay? So 30% of the time. So then he would be not late 70% of the time, because 30% and 70% have to add to 1. So when I multiply across the branches, I have 0.2 times 0.25. Okay, I wrote that backwards than what I said. Sorry about that. Actually, I'll just erase it and rewrite it because I don't want to confuse anybody. So again, we're going to go across the branch. Driving times being late is 0.2 times 0.25. So that gives me the very first probability of 0.05. Okay, then I go across the next branch, which is driving and not being late, would be 0.2 times 0.75. And so that one is equal to 0.15. Then the next branch would be biking and being late. So that's going to be 0.8 times 0.3, which is equal to 0.24. And then the last one would be biking and not being late. So that's going to be 0.8 times 0.7. And that's going to be 0.56. Okay, so the tree diagram part of it is over here. You don't have to do all the multiplying part to get credit for the tree diagram. But for part D, we can use some of those numbers that we just came up with. So this is find the probability that Raymond drove to work given that he is late. So I'm going to write it up here just because I'm out of room here. So I have probability that he drove to work given that he is late. That would be equal to the probability of driving and being late for work divided by the probability of just being late from work. So we're not even considering the days that he was on time to work because we are given that he is late. We are given that he is late, okay? So the probability that he drives and is late to work is the 0.05. The probability that he's just late to work would be the 0.05 or the 0.24, because both of those times, whether he drove or he biked, he's late for work both of those times. So we want to do 0.05 plus 0.24. Okay, so 0.05 divided by 0.05 plus 0.24 gives you 0.1724. So as a percentage, he is late. Let's see, he drove, excuse me, given that he was late, 17.24% of the time.